Why is nonlinear material stress analysis difficult? Imagine trying to predict how a rubber band or a piece of metal will behave when you stretch it really far. It's not as simple as pulling and knowing exactly what will happen. That's because materials don't always follow straight lines when they deform. When stress and strain relationships become complicated, understanding what's happening inside the material gets tricky. In linear stress analysis, everything is straightforward. Stress is proportional to strain, and material properties stay the same no matter how much you stretch or compress. But in real life, materials often pass their elastic limit and start to deform permanently. This is called plastic deformation, and it makes the stress-strain curve bend into a nonlinear shape. Once this happens, the material no longer returns to its original shape after unloading, and the stress depends on how the material has been deformed over time. One big challenge is that materials can behave in many complex ways. For example, some materials creep slowly under constant load, or they develop damage and cracks as they age. To describe these behaviors, engineers use advanced mathematical models called constitutive models. These models involve complicated equations that are not easy to solve. Another difficulty comes from the fact that nonlinear analysis needs iterative calculations. And like simple equations, there are no quick solutions. Engineers use computer methods like the Newton-Raphson technique to find solutions step by step. But these methods can have trouble converging, especially when the structure softens or buckles. This means the computer might struggle to find a stable answer, making the process even more complicated. Large deformations also change the shape and stiffness of the structure. This affects how loads are distributed and how the structure reacts. Contact points between parts may shift or change during loading, adding more nonlinearity because the forces at these contact points are unknown until the analysis is complete. Running these simulations takes a lot of time and computer power. They often requiring high-performance processors and large memory. This makes it hard to run many tests quickly, which is often needed during product design or failure investigations. Getting accurate results also depends on how finely the model is divided into small elements. To capture plasticity or damage correctly, engineers need very detailed meshes. Using coarse meshes can miss important stress concentrations, leading to less reliable results. Understanding failure modes in real-world products depends on nonlinear stress analysis. Many failures happen when materials yield or structures deform beyond elastic limits. But because these analyses are complex and computationally demanding, engineers often start with simpler linear models. They then add corrections or use simplified nonlinear methods to estimate effects. When detailed accuracy is needed, full nonlinear analysis reveals critical stress points and potential failure modes that simpler models can't show. In practical fields like crash testing, metal forming, or contact problems, nonlinear analysis is essential. It helps predict where and how materials might break or deform. The challenge is balancing the need for detailed, accurate results with the time and resources available. Despite these difficulties, mastering nonlinear stress analysis is key to designing safer, more reliable products and understanding how failures happen in the real world.